Can you hear me? Yeah. There you go. A little hard to see everybody back there, but thanks for coming out. I sure appreciate it. Would have been kind of strange if nobody showed up. My. Some nice pictures you've been posting on from the swamp. Looks like you just came out of the swamp. Oh my.
Happy Halloween, everybody. I'm not sure if you can hear me through this Halloween mask, but I'd like to thank you guys all for coming out today and braving this cold weather on this cloudy Halloween evening. Is it? Well, that's good. I see the moon up there, so that's a good sign. I don't know if you've heard the rumor going around, but we do have a blue moon going on this evening. If you do notice, it is not blue. Blue moon's basically just the term for the second full moon of the month. In addition to that, I have a lovely sales desk right behind me here. We have our 2021 calendars available inside. So if you'd like to purchase one after the program, we do ask that you enter the shop one at a time, unless accompanying a young adult. Other than that, guys, this is our last program up here for the 2020 season. So we'd like to thank you guys for coming with your face masks, chairs, making your reservations, and adapting to the new COVID precautions that we had to take so we could open up this year. With that being said, keeping with the Halloween theme, a very scary individual to my right, Mr. Walt. He's going to be telling us about how scary of a place the universe is. With that being said, I'm going to turn it over to Walt.
Thanks a lot, Matt. And again, welcome. Thanks so much for coming out here on this crisp, cold evening and joining us. And that wasn't directed at the people on the internet sitting in their warm living rooms watching me. But I thank you too for coming as well. As Matt said, it's a blue moon, but it's not blue. Does anybody know why we call it a blue moon?
I gave you the answer.
He gave the answer. Because it appears it's the second moon of a month. Whenever that appears, it's a blue moon. And there's a saying, once in a blue moon, which is supposed to be a long time, but actually we get a blue moon every 18 months or so. But it hasn't been until 1944 that we had a blue moon on Halloween. So that's kind of a lot of groundbreakers today. This is the first time I've ever given a presentation in a winter jacket. So that was a groundbreaker as well. And back in April, I did a presentation. We were just starting to do stuff live again, and we weren't coming out here yet. And I was in my living room with my cell phone taking a picture of my TV screen, which had my slides, and I was narrating the talk off screen. That was another first. So UACNJ has given me a bunch of firsts this year. So anyway, I named my talk "The Universe is a Scary Place," basically because it was Halloween and I wanted to keep a theme. But the universe can be a little scary if you really think about the scale and the power of some of the stuff that we'll be talking about, especially with the 2020 mindset of, what's next? Is an asteroid going to hit us, or, who knows? So my list of objects to discuss today, some are beautiful objects that were caused out of cataclysmic power, and some of them are just look a little scary, and some of them are so powerful that they actually are a little scary if you really stop and think about them. So this photo here that I have up, that's a wide-angle view of a reflection nebula in the constellation Cepheus. and it's about 1,500 light years away from us. It's known as the Ghost Nebula. And with the wide-angle view, you can see some of the accompanying goblins in the photo. So kind of a scary, moody view, but that's one of the objects that looks a little scary, but is not. It's just a lot of dust clouds that is set off by starlight. That's why they call it a reflection nebula. There's no inherent light coming from those nebula. They're just reflecting or lit up by starlight. Well, before I go on any further, let me just cover a couple housekeeping rules. We ask that you maintain a social distance from other attendees, use face coverings, please follow the guidance of our volunteers. Look up and enjoy the program. We've got a blue moon and we've got Mars, so if I bore you a little bit, you can just look right up there. We also got Saturn and Jupiter on the other side there. If you're so inclined, we'd appreciate any donations that you'd like to make to keep us going. We have a sales desk right next door to me. Credit cards and cash are accepted. Feel free to ask questions not only of me, but of our volunteers once we break. I think we're going to get some time to do some observing. Avoid using white light flashlights whenever possible. Cold beverages are next door. We've got a porta potty that's right there with the red light. And use your car's headlights. Don't worry about it. Safety comes first. So when you leave here, put your headlights on as you're driving out. Visit our website, like us on Facebook, follow us on Instagram, and please come again. But this is our last session of the season. We'll open up the first Saturday in April again. So one other thing we're going to be doing tonight is doing a little time traveling using just a telescope. Does anyone have any idea how we're going to accomplish that? I'll give you a hint. When I showed you this picture, I said it was 1,500 light years away. So what did I mean by that? Anyone? Exactly. It took the light from this Ghost Nebula 1,500 years to get to the camera that took this picture. So we're not really seeing the Ghost Nebula as it appears today. We're looking at it as it appears 1,500 years ago. And so when we use a telescope, the further away an object is light years wise, that's how far back we're looking in history. So telescope can really be thought of a time travel machine. This is the farthest known galaxy in the universe that we've discovered so far. And it's got that enticing name of MAC, blah, blah, blah. It's about 13.3 billion light years away from us. Right? So that's believed to have formed about 420 million years after the universe came into being. So the light from this galaxy, and you can see in the box up above, that light has been traveling to us for most of the age of the universe. And when we look at that, we're looking back 13.3 billion years in time. And so scientists can look back at these galaxies, these primordial galaxies, and get an idea of how galaxies form by just looking back in time. And you know, as our technology improves, the discoveries are just amazing out there. We're just learning so much more about the universe because we can see and measure things that are much farther away and delicate. Let's take a look at the talk about the spectrum. This is just quickly, this is the electromagnetic spectrum. Over here we have radio waves on the long end. We come down to like a TV remote control. We only see a little tiny bit of the electromagnetic spectrum. And as we go here, we get into UV light, airport security scanner, X-rays, gamma rays. As the wavelengths get tighter and tighter, smaller and smaller, there's more and more power there. And the universe radiates all kinds of different radiation. So when you take a picture with a camera, you're taking a visible light picture. So you're covering this much of the electromagnetic spectrum, that which you can see. But now we can put instruments on the Hubble to measure different wavelengths and really get some more information. Take a look at this. This is an a picture taken by the Hubble. It's the Eagle Nebula. And these have been nicknamed the pillars of creation because they're gas clouds that as they condense, the gravity gets higher and pulls the dust in more. And finally, they get hot enough that nuclear fusion can take place and stars blink into existence. So this is like a birthplace for stars. And this is what we see when we point a Hubble instrument that measures visual light, a regular old camera, at the Eagle Nebula. The Eagle Nebula is about 6,500 light years away. So we're seeing this nebula as it was 6,500 years ago. It's in the constellation of Serpens. Now this slide, the exact same field of view, but with infrared. It's sensitive to the infrared part of the electromagnetic spectrum. Very different. It can see through a lot of the dust. Not all of the dust, because that's really thick dust that we're looking at there. But it shows us a much clearer picture of some of these stars that are being born because we can see past the dust just by changing the wavelength that we're observing at. Here's a side-by-side comparison. Visible and infrared. Very cool. Now let's go wide field. We're going to look at the same area, but much wider view. So here are the pillars of creation that we're just looking at up close. So you can see we're seeing a much wider view. When we're looking at this picture, this is about 4 light years. So it takes light 4 years to travel from here to there. Obviously, that's a much bigger area. 70 by 55 light years. So it's an astounding amount of space. Although from here, it's still just a pinpoint. You know, the period at the end of a newspaper covers about the same area that we're looking at here. But you can see it's just amazing. You see a young star cluster to the upper right, NGC 6611, that you could see with a modest telescope from your backyard. It's not a tough object to find. But these pillars are being sculpted, you know, just as we see geologic formations that are crafted by erosion, right? If you see a stone pillar, it's not a stone pillar, it didn't grow up from the ground. It was cut away by erosion. Well, photoevaporation is taking place here. These young, strong stars, again, another 4 light years or so away, are raining down radiation, and these are the strongest parts of the dust cloud that were there, and they're still standing against that radiation. And that radiation is what's illuminating that cloud as well. And just think about it, 4 light years. You know, the closest star to Earth, Alpha Proxima, is about 4 light years away. So when you look at the density of all these stars within a 4 light year radius, this is much more packed, much brighter. I mean, there's no nighttime there. There's just too many stars for that. So photoevaporation is occurring there. And this is actually infrared and visual combined together to get this. And when you take an infrared, you have to put some false color in there so you can see what's going on. So here's a cool thing. Earlier mid-infrared images from the European Space Agency's Infrared Space Observatory and NASA's Spitzer gave scientists data that make them think that one of those stars in that star cluster probably went supernova about 6,000 years ago. So if that's true, what we're looking at right here doesn't even exist. There's no way those pillars would hold up to a supernova. This whole area of dust clouds would just be blown far away. But it's going to take us about 500 years to find out if the scientists were right about that. So be patient. So I started our journey with the Eagle Nebula because it combines beauty, it combines power, and the implications of time travel as you're looking through a telescope. Things can change by the time the light gets to us here on Earth. Anyone know what that is? What type of object? Yes. That's comet Hale-Bopp. I actually got to photograph Hale-Bopp right from our lawn here in 1995. And a comet has two tails. The ion tail, which is the light gas that's coming out of, it's basically a frozen snowball with dirt in it. And as it gets closer to the sun, the tail gets longer and longer because the sun is melting it. And so the ion tail always points directly away from the sun. The dust tail, the particles are heavier, so they're affected more by motion. So we could see from this tail going this way, this comet was traveling this way. And by the ion tail, the sun was right in that direction. Beautiful objects to look at. Usually not too worrisome, but they do have power. They can be a little scary sometimes. Like Comet Schumacher-Levy. Comet Schumacher-Levy was first detected a little earlier than Hale-Bopp, about 1993. And when they detected it in 93, they realized that the comet had broken apart due to the gravitation of Jupiter, broken apart about a year earlier, in July of 1992. And during the close approach, Jupiter created a tidal force. That means the gravity on one side of the comet was so different from the gravity on this side, it just kind of tore it apart. Because Jupiter is a very large, it's our largest planet. So it had broken apart. And then over a period of several days, centered on July 1994, the fragments of Comet Schumacher-Levy slammed into Jupiter. And those dark plumes are the result of the comet slamming into Jupiter. Each of those round circles is about the size of the Earth. So that's a little scary if it was Earth. So they hit it at a speed of about 36 miles per second. And the plumes went thousands of kilometers high. They left hot bubbles of gas. And actually when it happened, it was pretty cool. It actually happened on the other side of Jupiter. And astronomers had to wait for Jupiter to rotate into position so we could see those plumes come into view. And that, again, is visible light photograph. The largest fragments were about 2 kilometers in diameter. It was the first time humans ever saw objects outside of the Earth, but in the solar system, collide. It's known as an extraterrestrial collision of solar system objects. And this is a composite photo, a bunch of photos put together of the incoming comet fragments of Comet Schumacher-Levy. So, interesting, Jupiter kind of acted like a vacuum cleaner, as it does in a lot of things, protecting Earth from incoming stuff. So this is, I guess, almost a cousin to the comet. It's not a dusty snowball, it's just a chunk of rock that moves around the solar system. Anyone know what it's called? Asteroid. Thank you. Asteroids, they move around as well. And this is actually a radar image taken at a facility in Puerto Rico. It's about 2 kilometers in diameter, so about the size of the largest piece of Comet Schumacher-Levy that broke off. And on April 29th of this year, 2020, of course, it passed at a safe distance about 4 million miles away from us. So that's about 16 times the distance of us and the moon. So another 16 times that. It's the biggest asteroid to fly by Earth this year, and that we know about so far. I mean, you don't always see them. So we've got asteroids which usually behave themselves, but still, since they're flying around in orbits that can be changed, a little bit scary. This might be a little sensational, but there's some, if you surf around the web, you'll find a list of asteroids that might hit close to Earth. When they say hit Earth, NASA tracks anything that comes within that 4 million miles, like from here to 16 16 times the distance to the moon. And there's a whole big list of them. Nothing to, you know, lose any sleep over. But Apophis is a asteroid that made the news recently. The TVs were saying that, you know, around 2060, give or take a few years, this could come really close to the Earth. It's projected to come about 19,000 miles to our surface. 40 years. I'll be about 100 years old. So as an astronomer, that would be a really cool way to go out, wouldn't it? Anyone under, you know, anyone 20, maybe not so cool. But yeah, we'll see. You know, the calculations are so precise that they said it was coming closer. The reason why it made the news is because one scientist learned, and I forget the name of the effect, but there's an effect that the sun has. Just the heating of the sun on an asteroid moves its orbit just a couple of feet. And so they did the calculation that to figure out, you know what, I think it may be coming closer than we first thought. And then all of a sudden it made the news, because the news loves to pick up any sensational story to get you watching. So let's start talking about stars and the life of stars. And I do a whole hour on the life of stars, and I will spare you. But I'm going to talk about some of the objects that are left behind, both explosions and just stars going into old age. You start out with a stellar nebula, like the Eagle Nebula, where you have a bunch of dust, and the dust starts collapsing, the gravity starts taking over, and finally you get some nuclear fusion if there's enough gravity and enough mass. And then it lights up. And there's two forces that are battling each other. There's the radiation from the fusion is trying to push the star out, and gravity is trying to pull the star in. And sooner or later, after a few million years, you get into what they call hydrostatic equilibrium. And that's when the star finally, the gravity and the radiation balance out, and the star's kind of found its size, and it stays there at that size. They call it the main sequence on the Hertzsprung-Russell diagram. So it'll stay there most of its life. And that you see the average star. So the sun, and anything up to about 8 suns, it'll burn hydrogen. When it runs out of hydrogen, it'll start to burn helium, and it starts to become, the gravity starts to loosen up a bit, and you get the outside expanding into a red giant. So a star like Betelgeuse, if that is a red giant, it's near the end of its life. And if it was where our sun was, everything up to Jupiter would be swallowed up inside of Betelgeuse. So it gets pretty big. Our sun is going to do the same thing. When it becomes a red giant in another 5 billion years or so, we'll be inside it. So we're about halfway through the lifespan. A star the size of our sun lasts about 10 billion years. It's about 4.5 billion years old. So it becomes a red giant, and then you get this helium flash where most of the mass collapses into a white dwarf, and you no longer have atomic fusion. It's just a really hot ball that's going to take billions of years to cool off. But it leaves behind a planetary nebula. So at the end of our star's life, and anything up to about 8 times the size of the sun, we'll end up with a planetary nebula and a white dwarf. The white dwarf's in there. The planetary nebula finally blows off, and you're left with just a white dwarf that will spend billions of years cooling off. But the planetary nebulas are just unbelievably beautiful. There's a picture of the Ring Nebula. It's about 1,630 light years away in Lyra. In the summertime, it's directly above our heads, and you can see it as a little tiny smoke ring through telescopes right here. It's very ordinary glowing remains of a sun-like star. That's how they look. But we'll see different variations. 15th magnitude star means that you've got to use a telescope. And it's the size of a planet. From the size of our sun, the white dwarf becomes the size of a planet. So it's very, very, very dense. Super high density. It's about a metric ton per cubic centimeter. And then different colors represent different different elements. The blue is helium. The cyan color of the inner ring is hydrogen and oxygen, and the reddish outer ring is from nitrogen and sulfur. The ring's about 1 light year wide. The planetary nebula phase, that smoke ring, lasts only about 30,000 years or so, and then it just slowly dissipates. It just keeps, the gravity's not enough to hold it, and it just floats away, and then you just have your white dwarf. Again, we talk about different wavelengths. So if we add some infrared and look at this and add it to this visual image, look what we get. That's the original image that we were looking at. And this was when it was in its red giant phase. That's what's left behind. It's the residue of stellar winds. And you could see, you could see the motion right in that picture. In the red, you see the lines radiating outward. You could see that there were some stellar winds just blowing that gas out from the star itself. So that happened about 10,000 to 100,000 years before the white dwarf appeared. It was from the red giant phase. Here's another. I'm going to look at just a couple of planetary nebulas because they're pretty cool. They were formed out of violence. They're warm, but they're not what I would say dangerous or scary. They're really beautiful, and it's beautiful to think that they were formed out of such a death throes of a star. So this is the Dumbbell Nebula. That's about 1,200 light years away from us. That one's called the Hubble Spirograph. I don't know if anyone remembers a spirograph. I think they still sell them. Images is from the year 2000 from Hubble, and it has a more boring name, IC418, but it glows like a multifaceted jewel. It's very intricate, all of the structure that's in that cloud. And remember, when we're looking at these, it's really surrounding the entire star. It's not like a flat, not like the rings of Saturn where it's flat. I mean, we're looking at this. But these colors are surrounding the entire white dwarf. It's a globe kind of thing that we're looking at. It's hard to imagine it in only 2D. Here's one that qualifies as a strange object. Again, it was formed by the same processes, although we don't really understand exactly how this Cat's Eye Nebula came to exist as such, because if you look at it, there's 11 or more concentric rings. You see those rings? It's kind of like if this was an onion and we cut the onion and we have all of these distinct rings, and scientists have no idea why this formed so much differently than your average ring nebula. There's been all kinds of theories, of course. There's no shortage of that. But it looks like they were formed at 1,500-year intervals. So some scientists think it might have been magnetic pulsations. Some people think it might have happened after the envelope occurred, that the magnetic fields might have oriented it into rings. Nobody knows for sure. I'm just thankful that there's no alien theories behind that one. But those bullseyes came as quite a surprise to scientists. At the time this was discovered, they had seen nothing like it, and this was just one of those boring old planetary nebula. So and then you can still see that there's a dwarf star there. It's the dead core of of a star, just like our sun. And again, it's approximately the size of the Earth. That's about the size of the white dwarfs, give or take. So our sun right now is so large that about 1,300,000 planet Earths could fit inside it. That's the size of the sun. So imagine half the mass of the sun in 1/1,000,000th the space, right? Because that's what we're talking about here. 1.3 million Earths inside the sun, but half of the mass of the sun, when it becomes a white dwarf, ends up the size of the Earth. So you can imagine how thick and dense it is. As I said, it's about a metric ton per centimeter. Kind of hard to pick up even a teaspoonful of this stuff, if you could get close enough to it, of course, right? And then, just like other ring nebulas, in a few thousand years, this gas shell is going to disperse, and we'll just be left with a white dwarf. Okay, this pretty planetary nebula is called a little ghost nebula. So there's a little more Halloween theme for you. Because it's round and very faint. It's about 1 light year across in the shell. Small ring structure, ionized oxygen and hydrogen. And it does look, when you look at something like this through a telescope, your eye is like a 1/30th of a second shutter speed. So when you look at something, except for maybe the bands on Jupiter, you're not going to see colored. What you're going to see is light, smoky color. Well, not even color, just a smoky apparition. So this really does look ghostly when you look at it in a telescope. Your eye just can't gather enough light to see the kind of colors that we're seeing here. You've got to have a shutter of a camera open and collecting a lot more light photons than your eye is capable of doing at any one time. Now this is a gorgeous, again, it's a planetary nebula. They call it a bipolar nebula, so that should give you a warning. It might be a little dangerous. And it certainly is. Again, it was formed similar to the way the other ones were, but it's one of the most complex structure in this type of nebula. And although it looks beautiful, there's a tremendous amount of power behind that beauty. The spectrum of the center star shows it to be one of the hottest stars known, with a surface temperature of about 250,000 degrees Celsius, 450,000 degrees Fahrenheit. Compare that with just under 10,000 degrees Fahrenheit of the sun, right? So we're talking about 450,000 Fahrenheit compared to under 10,000 Fahrenheit to our sun. That's hot. That's really hot. It must have been a big star, and right now it's only 64% the mass of our sun. The central star itself can't be seen because it's hidden in a band of dust. It's like a donut-shaped ring of dust, and that's why you're seeing the clouds, and the energy is directed in a bipolar area, because that dust ring is kind of choking it. The outflows of this, though, are roiling cauldrons of gas heated to more than 36,000 degrees Fahrenheit and racing across space at more than 600,000 miles per hour. So we see this beautiful, beautiful object, and the amount of power and heat and intensity and just the speed of the particles moving is mind-boggling. I mean, it's and very dangerous, right? Kind of scary, but from afar, it's just an absolutely stunningly beautiful object. So we've looked at the remains of stars from a sun about our size, a star our size, the size of the sun, as I said, up to about 8 times larger. When you get a little larger than that, you take the bottom route. You start out the same, but there's more mass, so you have a more massive star. And the more massive a star, the shorter its lifespan too. On one end, you have the brown dwarfs, which scientists estimate could last trillions of years, but we don't know because the universe is not that old, and so we've never seen one die out. But on the other end are these supermassive hot stars that die out in millions of years instead of billions of years. And so when you have something more massive than 8 times the sun, it ends up in a red supergiant. And then it goes supernova. What the difference is that it burns more elements. Where one of the, on the top path, you might stop around carbon. The bottom will keep going until it hits iron. Iron is the stopping point for all stars. You can't go past iron in fusion because iron takes more energy than it gives. And when you get to the supernova stage, when you get to iron, within a second of iron going in the core, you get the collapse and then this super explosion. And where one star exploding like that can outshine an entire galaxy. And this is a very simplified explanation. The more we learn about supernovas and stellar evolution, the more scientists want to redo the entire classification system, because the classification system for supernovas was over 100 years old, and our instruments are now showing such different variances in the life of stars. They want to do some renaming, so that's like an ongoing battle. But anyway, very simply, you get a supernova, and in most cases you're going to end up with a neutron star. That's what I just described is known as a type 2 core collapse supernova. There's all type 1, type 1A. They've got a whole alphabet now. But very simply, that's what results in a neutron star. Again, these explosions are so bright and immense that they're visible at immense distances. If a nearby star were to undergo a supernova explosion, it would be bright, so bright that it would be visible during the daytime. In modern history, we have not seen that. However, astronomers in the 17th century, Tycho Brahe and Johann Kepler, they observed naked eye supernova in much simpler telescopes than we have today, and during the daytime. In '87, a supernova went off about 50,000 parsecs away from us, which is about 163,000 light years. And that's what I'm showing you there, supernova 1987A. This picture was taken 2 weeks after the explosion. And I mean, the camera can't even capture how bright this supernova is. 2 weeks after it exploded, it outshines the galaxy that it's in, that entire area. And again, we're still studying that supernova and learning a whole lot about it, just the way that the shell's forming, and it's been a great opportunity to learn a lot more about supernova. This is an artist's rendition, just showing the core of that star collapsing and then bounces off, causing a huge shock wave, and you can see that shock wave depicted by the artist. It blows off most of its outer parts. But what's left is called a neutron star, which is even denser than a white dwarf. These things are crazy. They can have a mass greater than our sun and only be 12 miles or so across, like Manhattan. So imagine stuffing the entire mass of the sun into Manhattan. It blows my mind. The sun weighs 333,000 times more than the Earth. So imagine 166,000 Earths packed into the space of Manhattan. That's what we're talking about. I mean, you can't even imagine that. Even me telling you 166,000 Earths in Manhattan, you can't possibly imagine how dense that is and how hot that is. It's a tiny star that's approximately 1 trillion times more dense than our sun. This is a supernova remnant on a cosmic scale. This is in the constellation of Cygnus. It's called the Veil Nebula, and it's a supernova remnant. very beautiful. You could see those gases are still illuminated by the neutron star in there. The Veil Nebula spans about 3 degrees now. It's moved so far apart. That's basically, if you take the moon and put 6 of them side by side, that's about how much sky this Veil Nebula. It's a lot, obviously it's a lot fainter than the moon, but it takes up a large chunk of the sky. It's really spread across a large area. At the distance that it's at, which is about 1,500 light years, it translates to 70 light years across this Veil Nebula. So from one end of the nebula to the other, light takes 70 years to travel. This is one of my favorite objects. And again, it's a supernova remnant with a pulsar right in the middle. And it's called the Crab Nebula, M1. This is a mosaic image put together by the Hubble telescope. And again, it's a remnant of an explosion. I love the filaments that you see in this. But what I really think is cool is that this supernova this star went supernova in the year 1054. And Chinese and Japanese astronomers did see this supernova during the day, and they recorded it. So, you know, when I'm looking at this, I think back only 1,000 years, man was still walking around on the earth. 1,000 years ago, there were astronomers that looked up in the sky and saw this thing go supernova and saw it during the daytime and kept the records that we have today. And it's just so cool. Now it's much dimmer. It's magnitude 8.4. It's very dim, but the neutron star is spinning very rapidly. It spins at 30 times a second. So imagine that dense star the size of Manhattan, the island of Manhattan, spinning 30 times a second. I mean, the amount of power involved there is just unbelievable. So, and the neutron stars it's called a pulsar because it's like a lighthouse. You know, a lighthouse, you see the light turn around and you get polarized radiation, bipolar radiation again, from this neutron star. And so as the radiation hits you, you could pick it up with a radio telescope. You could pick up those 30 bips a second as this thing is rotating around. This is a little closer view of the Crab Nebula. It's kind of stripped away using some infrared photography as well. And you can see the wisps moving away. You can see the gravitational disturbance just to the right of the middle, which is where the pulsar is. And it's forming expanding rings, almost like ripples in the energy. And again, so again, 30 times a second. This is another supernova remnant. I just love it. You know, obviously there's some processing going on here because there's some infrared combined with the visual field. But this is a remnant that shines bright, colorful streamers. Almost looks like smoke rising up on it. It's just so intricate. It's captured by the Hubble Space Telescope again. It's called N49 and contains a fast-spinning neutron star with a very, very powerful magnetic field. It's about 1,000 trillion times stronger than the Earth's magnetic field. Again, those numbers are so big they become meaningless. But obviously it would make your compass go crazy. This neutron star here spins every 8 seconds. It's also emitting X-rays and gamma rays. So the colorful filaments are just debris from that explosion. But there's still some very deadly radiation coming from this remnant. This is found in the Large Magellanic Cloud. You can't see it from up here. You have to be I think you can see it you can certainly see it in Hawaii. I think you can see it in Florida. Certainly see it in the southern hemisphere. It's an irregular galaxy that's very, very close to our galaxy. It's a naked eye galaxy from any place that you can see it. So here's another deadly object. This one's named the Black Widow pulsar. Again, it's a supernova remnant. And it's a pulsar with a companion star that's known as a brown dwarf. So it's a very dim companion. It's about the same size as the other pulsar, about 12 miles, size of Manhattan. But the Black Widow is a very dangerous partner to have. The two stars orbit each other at every 94 minutes. So this is a very, I mean, try to imagine two stars orbiting each other every 94 minutes. And while this is happening, the pulsar, the gravitational force of the pulsar, is just stripping off material from the brown dwarf. And sooner or later, the brown dwarf is going to be totally evaporated. This is an actual photo taken in X-ray and optical, and it was made possible only by using the gas cloud around it as a magnifying glass. It's technology I can't even begin to understand. We're going to talk about gravitational lensing later on, but using the cloud to magnify this and get this picture is like seeing a flea on the surface of Pluto from Earth. That's the kind of resolution. Seeing a flea on Pluto from Earth is the type of resolution that you're looking at right now. You can see why astronomy is just advancing in leaps and bounds as far as what we know. This is 6,500 light years away. And this picture is very recent. It's from May 2018, so it's only 2 years old. The pulsar's beam, remember the energy beam, is just stripping layers from the brown dwarf. And then the pulsar's gravity just slurps it up. So it's the energy is stripping the material off the brown dwarf, and then the gravity is just sucking it up as it becomes more and more dense. Nothing is going to be left after a while. That's why they call it the Black Widow. Only the Black Widow will be left, and it'll be dancing by itself. This pulsar spins at 600 times a second. It's known as a millisecond pulsar. And just thinking of an object like this spinning 600 times per second gives me intellectual constipation. It's unbelievable. Let's look at an artist's rendition of it. Moving at 620,000 miles per hour, right? The sun's forward velocity in the Milky Way, the sun moving in the Milky Way, is about 45,000 miles per hour, right? So we're not only moving on an Earth that moves, but our entire solar system is moving too. And the solar system is moving at about 45,000 miles per hour. This system is moving at 620,000 miles per hour. And so you see that shock wave in front of it as it's cutting through space. Astronomers were actually able to observe two intense regions of radiation 12 miles apart on that, on both sides. 12 miles. The astronomers were able to actually detect these two intense regions of radiation, which is just mind-boggling how they can do that. There's another picture of the system, artist's conception, with the bow, the shock wave as it moves through the solar system. Okay, finally, we just looked at the neutron star, basically formed from suns that are stars that are 8 to 80 times the size of our sun. If they get much bigger than that, in their death throes, they're so massive, they collapse into a black hole, we think, right? I mean, as the objects get stranger and stranger, our actual knowledge gets more and more tenuous. But we have some interesting observations that back up the theory on that. This is an artist's rendition of a black hole. A black hole is so massive that it actually bends the fabric of space-time. Space-time, that sounds like Google. Space-time. And so you see near the event horizon, as it eats up mass of anything around it, it bends gravity such that the stars near it look like they're elongated. Some of the old elongated stuff is actually galaxies that are elongated, but a black hole is so massive that it bends the fabric of space-time. And there's some interesting stuff that happens because of that. But first of all, has anybody seen this picture? This was, a couple of years ago. Very, it made quite a splash because it's photographic evidence of a black hole. I won't say we photographed the black hole because light does not leave a black hole. And so photography is all about capturing light or electromagnetic radiation. But what we captured here was the event horizon, where mass is getting heated up and sucked into the black hole. And so the middle of that donut is the black hole. We're not actually photographing the black hole, but we've got the evidence that there is a black hole there. And that happened in April 2017. The picture was released. It took quite a while to create the algorithm that put that data together and give us this image. It's quite a team of astronomers. So that's a supermassive black hole that we see the evidence for right at the heart of M87, which is an elliptical galaxy in the Virgo cluster, which we can see. We can see the cluster in the summertime. We can see M87. We can't see the black hole, but this is the black hole's home. That's what M87. It's a nondescript galaxy, about 55 million light years from Earth in the constellation Virgo. And Virgo's got a ton of galaxies. It's one of the fun things in the spring to look at Virgo and look at the clusters of galaxies. But unlike the Milky Way stunning spirals, this elliptical galaxy is just like so ho-hum. There's really nothing much there, but it's got a pretty cool black hole that we were able to get a picture of. Now, we talked about using the cloud for lensing when we took a picture of that black widow pulsar. Einstein predicted that groups of galaxies would be so massive that they would bend space-time so that you could see objects behind them. And they call that gravitational lensing. And that's exactly what we're seeing here. This cluster of galaxies is so massive that there's a galaxy behind it that we're seeing here, very much distorted. The image is very much distorted. But that's a galaxy that's behind that cluster and that we're able to see because of a black hole bending space-time and letting us see behind it. This is my favorite picture of gravitational lensing. It's called Einstein's cross, and there's many galaxies. You can see how massive the galaxies are there, and there's a large cluster of galaxies, and we've enlarged it right in that box there. And if you look at this is a magnification of this. And if you look here, you see 4 dots here. Those 4 dots it's one event. It's a star going supernova behind the galaxy, and 4 different, because the light traveled in 4 slightly different directions as it came out from behind the galaxy, we're seeing the supernova in 4 areas in the sky because of gravitational lensing. Just mind-boggling. Einstein predicted this, and we finally got to the point where we have instrumentation to discover it. You know, when Hubble first went up, we would point it at what looked like empty areas, and we'd do like these deep field surveys, and we'd be amazed at how a section of the sky where it looked like there was nothing, we would see 1,500 galaxies pop up in the space of a period at the end of a sentence in the sky. But now what they're doing is they're pointing the Hubble and our instrumentation at crowded parts of the galaxy, of the universe. And we're looking at these gravitational lenses, and we're seeing beyond those objects to what's actually behind it. And to see a supernova like that through gravitational lensing is just unbelievable. I think I read, it's been a while since I put this in my collection, but I believe there was a prediction that 5 years after this picture, they were going to see another occurrence from the supernova because of a different light path. Don't ask me how a Poindexter can calculate that, but that's the prediction, and that's only 3 years away from now. So we'll see if that scientist is right. Here's a Halloween themed gravitational lensing for you. This is called gravity's grin. These are distant galaxies that are seen through the looking glass of both X-ray and optical imaging. It's from Chandra and the Hubble Space Telescope. It's also nicknamed the Cheshire Cat for obvious reasons. The group's two large elliptical galaxies that you see in purple, which is the X-ray portion of the picture, are framed by arcs, and those arcs again are gravitational lensing. So the arcs around that head, the mouth and the side, that's gravitational lensing of galaxies behind these two massive galaxies. And these two galaxies that form the eyes are merging together, right? The relative collisional speed of about 1,350 kilometers per second heats that gas so that it's visible in the X-ray part of the spectrum, and it shows in purple hues. The Cheshire Cat group grins in the constellation Ursa Major, which is about 4.6 billion light years away. Now, Ursa Major is a constellation, but it holds a very famous asterism or group of stars. Does anyone know what it is? Yeah, Big Dipper. That's right. Ursa Major is the Big Bear, and a major part of Ursa Major is the Big Dipper. So that's the direction that gravity's grin is smiling at us from. Okay, a couple of, we've been looking at remnants from cataclysmic explosions and just stars dying. Now we're just going to look at a couple eerie pictures from gas clouds that we've taken pictures of, with the Halloween theme, of course. So here's the Ghost Nebula. It's a reflection nebula, meaning that it doesn't have inherent light itself. It's being lit up by a star behind it, and by the energy of other stars. It's located about 1,500 light years from us. This is the same nebula, a little different view. It's considered a globule, and it's over 2 light years across. There's several stars embedded in it, and it's the emissions of those stars that are giving it that brownish color. And then back to our original shot. This is a much wider view of the same area, but it's the Ghost Nebula with a bunch of goblins. It's a much wider crop, showing a much more extended region of nebulosity. Kind of eerie. I don't know if it's scary, but it's kind of eerie. Here's another eerie picture of some flowing shapes. This is in the constellation Cassiopeia, which looks like a big W and is close to the Big Dipper. It's a colorful sky shape. The clouds are almost comet-shaped. They're about 600 light years away from us. And no, they're not really ghosts. They're just dust clouds. And they're slowly disappearing under the influence of energetic radiation from from the luminous star Gamma Cassiopeia. This is called the Great Carina Nebula. It's a jewel of the southern sky, and it spans over 300 light years. It's one of our galaxy's largest star-forming regions. Again, this is within our galaxy, not outside of our galaxy. Kind of like its cousin, the Orion Nebula, which we get to see, which is also a star-forming region. The Carina Nebula is easily visible to the unaided eye. And if you see Orion, which will be coming up in the winter, if you use binoculars, you can see the Orion Nebula. If you're in dark skies, you can see it naked eye. But around here, where the sky has so light polluted, a lot of times you've got to use at least binoculars. This is about 7,500 light years. And what's really cool about that is this baby, this star, Eta Carinae, is embedded in it. They've used all kinds of digital processing techniques, which I totally don't understand, to get this amazing high resolution image of this star. Again, you can see it's bipolar, right? There's two globes of energy. It's about 8,000 light years away, but we can see structure only 10 billion miles across, which is the diameter of our solar system. So that's really high resolution in astronomy. And this star was supposed to have gone supernova in the 1800s, 1860 something. It was a bright flash, but it never actually went supernova. It's still a star, a very hot star. And even though it had that outburst 150 years ago, it's still surviving. And it's one of the brightest stars in the southern sky. It's a massive star, and it released as much light as a supernova explosion 150 years ago. So scientists, this is really a cool star to look up if you want to look into astronomy and look at some strange objects. Eta Carinae has a great story, which I will not go into at depth, but it's a real puzzler. And again, massive energy. I mean, you could see this has more infrared information, and you could just see the energy coming out of that system. So let me just switch gears for a second. When you get out there to observe in just a couple minutes, take a look at the moon. You can see Mars. If you walk out in that direction, you'll be able to see Jupiter and Saturn, most likely. I haven't kept an eye on it, but it's that way. You'll see. Okay, so we'll get out there quick. Two last pictures to leave you with. There's the Great Pumpkin. It's actually a collision, again, of two galaxies taken by the Space Telescope. And then finally, this is a really cool shot. Two more galaxies that are colliding. And they're in the middle of a head-on collision. And the blue rings and the nose and the mouth are all hot young stars. And they're clumps of stars that have just formed because of the interaction of these two galaxies. And that ring structure that outlines the face will be gone in about 100 million years. So hurry up and get your telescopes out. But the merging of the galaxies is going to take another 1 to 2 billion years. And that comes from NASA. Most of these pictures that I have come from Hubble Space Telescope Jet Propulsion Lab. You can Google and get all kinds of great stuff on your own. And I hope some of you will take the time to do that and look into it. That's my greatest hope giving talks, is that people will be encouraged to take a look at astronomy and just Google some stuff and read some Wikipedia. It's just an amazing field. And unlike Star Wars, this stuff is all real. It looks like science fiction, but this is real stuff. When you look at this and you explore this, you're doing real science. You're learning about science. There's even a place called Galaxy Zoo where you can help scientists sort out galaxies and classify galaxies because they need help. They have so much data, they don't have enough people to sort through it all. So thanks so much for coming out in this cold weather and listening to me and I'm glad that the sky's cleared out, so you might be able to see a few cool things on our monitors. If you so move to make a donation, that helps us keep going. We have our sales desk. Again, ask questions. Try to avoid using white light flashlights. We kind of, I don't have my red handy. Red lights are the best. We've got people who have lights around, and that moon is so bright it's just about going to throw a shadow. So it shouldn't be a problem. And come again, April, we open back up every Saturday. Maybe we'll be able to do it without masks. Who knows? So thanks a million.
All right. Thank you, Walt. Thank you guys for coming out. Can you hear me? Because I know I'm muffled because of the mask. All right. It is Halloween. I know some of you opted to come here instead of going trick-or-treating. So, because I spend way too much time on the internet, we have Yeet the Treats. So I have treat bags for everyone here. So, yeet!
Yeah, I said this was going to be bad.
Yeah.
Ooh.
Donation so we can keep our insurance policy up.
All right. Are there any questions? Perhaps some of you might want to come closer because I'm really bad at throwing, as we've all noticed now. All right.
I'd just like to mention, you didn't, what do you call it? I think you fulfilled what I came out to hear, and that was that you said about scary universe.
Yeah.
And out of the 3 questions I had, you hit 2 of them.
Wow.
And right off the bat, it was about asteroids, but more specifically about Apophis. Is that how he pronounced it?
Yeah.
Apophis. And I was hoping maybe you touched on it. And my biggest concern was that recently I've heard something about it. And again, the size of it, about 4 to 5 football field length, width, whatever. And you brought up about the weight of some of the, what do you call it, the material of these asteroids or planets.
Yeah.
But the thing that got my attention was that when it comes through space, that'll knock out satellites, 1. 2, it's supposed to hit somewhere in the Pacific Ocean between California and New Mexico. And 3, it's got the potential of 65,000 atomic bombs. Now, scary, that all sounds scary, but one thing that really bothered me was when I heard them say that NASA is not being straight with us. 2029. And then somebody said to me, hey, listen, if you really want to get a handle on it, you ready for this? Go to Revelation 8th chapter. NASA called it Apophis. There, it's wormwood, right? And then it gets better because then you brought up Virgo. And so I don't know if you're familiar with September 23rd, 2017, Virgo, when they had NASA actually redacted something, and it is on, like you said, you can go to Google, you can look it up under Virgo constellation and take a look at what was redacted. And what was redacted looked very similar to, you said, the Siamese cats. It was supposed to be the dragon. Same thing. Person that told me about the wormwood said, listen, go to Revelation 12. And I said, and if you do it yourself, you'll say the same thing. Oh my God, there it was. So it's all there, and it's, I guess, kind of scary. And somebody said that science is back there catching up to what's already in the scriptures. And the last thing was, you didn't touch on it, but you're probably familiar with the blood moons.
Mm-hmm.
And that according to NASA, the last series of blood moons was on April 3rd, 2014. And it was interesting because that was the start of Good Friday and Passover. And it's interesting because when did the blood moon start? When Jesus Christ was crucified on the cross. And so for what? Yeah, there was. I mean, do you feel with well, go back to Apophis? I know you said that it may not be this early. Do you think that NASA's holding back from us?
I think they're still trying to figure out all of the mechanics involved in accurately predicting where it's going to be. And the best science right now says it's going to be about 19,000. It's going to pass 19,000 miles from us. Yeah,
It's not the only asteroid that has a potential.
yeah. No, I showed a whole list of them
Bennu,
up there.
You said Bennu.
Yeah.
NASA just ran a mission to sample Bennu. Literally.
Crash
2 days
into it.
ago.
Yeah.
And it didn't crash into it. It had a tag. Touch and go. Your refrigerator?
Okay.
They can lift the
right.
refrigerator? I'm not sure what they call it. I knew it. The site that they sampled was called nitrogen. And it actually sampled more than they had expected to sample.
Okay.
It was actually more successful. It was so successful they had trouble closing
The
the
hatch.
container. Now they did finally do it. It was leaking puts the Bennu out. But Bennu was calculated to be a 1 in 270, getting us maybe 100,000
Yeah.
years down the road. Apophis was given a chance of hitting us earlier, but it obviously didn't happen.
Right.
And I think the Japanese ran their Hayabusa satellite collection similar to what we had with Bennu, and they're going to bring samples of Apophis back.
Mhm.
So, so it's still in the works. Yeah, I mean, that's one thing they're sampling, and one thing that hasn't been brought up that was something to be